So welcome to One-Dimensional Forces. This is the lesson that we did do in class before we did our lab, and I'm hopeful that you're watching this video. We're going to go through what we did in class, and you can watch this video as many times as you like. That goes right along with the notes. So gravity always points downward and is constant. This is something that you have known before you came to physics, and gravity will never leave us. You will never have a day without gravity on Earth. So we have to acknowledge it. It's also constant, which means that it is the mass times the acceleration due to gravity. We call it Fg equals mg. M for mass, g for acceleration due to gravity, which is negative 9.8 meters per second squared. The scale in this in this PowerPoint is going to represent the normal force. The man exerts a force on the scale, and the scale exerts an equal and opposite force on the man. So he's standing on the scale. We're going to use this scale to look at the normal force, and the scale is going to change as he accelerates or upward or downward, but his weight, which is mg, is never ever going to change. So let's go ahead and take a look at our free body diagram. And on our free body diagram, you see Fn, normal force, and that's a contact force, is equal to 500 newtons in the upward direction, and Fg is equal to 500 newtons in the downward direction. Notice there is no negative sign for that downward direction on a free body diagram. So right now the elevator is at rest. Acceleration is equal to 0 meters per second squared. That means the summation of our forces in this statement right here, sigma, sum of, F for force and Y for the vertical direction, equals 0. So Fg plus Fn. Fg is equal to mg, mass times the acceleration due to gravity, sine 270, which makes it negative because it is going in the downward direction. Fn, the normal force, is equal to mg sine 90, which is equal to 51 kilograms times 9.8 meters per second squared. On our free body diagram, it's the same one. They are equal to each other in magnitude because the elevator is at rest. Mass of the person would be 51 kilograms, but that person is not accelerating. So because they're not accelerating, the ma goes to 0. If we drop the apple falls at a constant acceleration of negative 9.8 meters per second squared. Okay, so now we're going to accelerate this elevator upwards. So we're going to have the acceleration is going to be 2 meters per second squared. It's going in the upward direction, so the acceleration is going to be positive. And force, we're going to write sigma right over here, Fy for the forces in the vertical direction equals ma. 51 kilograms times 2 meters per second squared is going to equal Fg plus Fn. That is our summation of forces statement. Summation of the forces equals ma equals Fg plus Fn. Well, to find Fn, which is what the scale is going to read because the scale represents the normal force, we're going to have to do ma subtract Fg. So we end up with 102 newtons. So when we multiply kilograms times meters per second squared in the magic world of physics, we get the magic thing called newtons. Newtons is the unit of measure for force. So that would be 102 newtons. And then I'm going to subtract a negative 500 newtons, so I'm adding the two together. The force on the scale as you accelerate upwards is going to be 602 newtons. You're going to feel heavier. On our free body diagram, the magnitude of the normal force is going to be greater, so that it's represented in such with a longer arrow than gravity. Remember, gravity is constant. It doesn't change. It never will change on the man as long as he is 51 kilograms. So if we drop the apple's going to accelerate at negative 9.8 meters per second squared, but because the elevator is accelerating upwards, it appears, not falls, but it appears to fall at negative 11.8 meters per second squared from the man's perspective. But gravity doesn't change, so it continues. It is falling due to gravity at negative 9.8 meters per second squared. So now my elevator is at constant velocity. constant velocity, up or down, it doesn't matter, is not acceleration. So when I have the summation of my forces in the y direction equals ma, a is 0, so it's going to be vertical. So my normal force is going to equal the negative of the gravity force. So I end up with 500, normal force is going to equal 500 newtons. Gravity force is going to equal 500 newtons. Free body diagram was just like it was in the first slide. So now my elevator accelerates downward. It's accelerating downward at 2 meters per second squared, so that 2 meters per second squared is going to be negative. So A equals negative 2 meters per second squared. The summation of my forces vertically equals ma equals Fg plus Fn. Fn is going to equal ma subtract Fg. My ma is going to be negative 2 meters per second squared times 51 kilograms, which is equal to negative 102 newtons. So the normal force is going to equal negative 102 newtons, subtract a negative 500 newtons, and I end up with 398 newtons. So this is kind of similar to when you go on an amusement park ride, like the free fall or something that falls very quickly and you feel lighter. Yeah, the scale's reading that you're lighter because of your acceleration downwards. So on my free body diagram, the normal force is going to be 398 newtons, so that is represented in an arrow of lesser magnitude than my Fg. And my acceleration is pointing downwards. The apple would fall at negative 9.8 meters per second squared, as always, but because you're on the elevator that's accelerating downward, it appears to fall at negative 7.8 meters per second squared. But it's only going to ever fall at negative 9.8 meters per second squared. So our last scenario is going to be that the elevator is in free fall. So the cable snapped. Don't worry, there's a spring at the bottom of the elevator. We'll discuss those types of problems later in the year. So the elevator cable snapped. My ma, my acceleration of the man, is now going to be negative 9.8 meters per second squared. So my normal force is going to equal ma subtract Fg. My ma is going to be 51 kilograms multiplied by negative 9.8 meters per second squared, and that is going to, so that's negative 500 newtons. I'm going to subtract negative 500 newtons. So my normal force in this case equals 0. That means that the scale is not exerting a force on the man. You are both in free fall. So we don't draw the normal force in because it's equal to 0. So the only force acting on the man at this time is the force due to gravity. The apple would still fall at negative 9.8 meters per second squared, but it would not appear to be falling. It would appear to be floating because both the man and the man and the apple are both in free fall. So that concludes what we did in class. There's another video on the lab. I hope you watch it, and you may ask me for any questions. Thank you for participating.